Let's start by taking a look at our gear pumps, specifically the external gear pump. The external gear pump works in 4 different stages. First, at the inlet port, a vacuum is created as the teeth unmesh. This vacuum pushes oil from the hydraulic reservoir into this large primary chamber at the bottom. Then, as your gears spin, the oil is carried around the housing in chambers formed between the teeth and the housing side plates. We can see that the oil is located in these small little pockets here, and as the gears rotate, they travel around the housing, and eventually, when the teeth unmesh from the outer housing, are deposited here in this larger chamber connected to the outlet. Because the teeth of the gears squeeze together here in the middle, this creates a pressure and pushes the fluid out from the outlet. Note that because of the pressure on the outlet side, the gears experience a high force that pushes into them at a sort of diagonal direction represented by this arrow here. As such, when designing teeth like this or pumps like this, we need to make sure that these gears can withstand the force of the outlet pressure, which is why they're typically manufactured out of metal instead of simple plastic or weaker materials. We can kind of clarify how this works by looking at this animation. We see on the blue side here on the left, the inlet, which is coming in at a low pressure, and as the hydraulic oil flows through the system, we see how it gets packaged into these small chambers and pushed around to the outlet of the housing, right? And then, as the gears remesh together here, it squeezes the fluid out, creating a pressure and forcing the fluid out of the outlet port. Now, this leads to a few pros and cons. Notably, external gear pumps operate at a high speed and can handle a high amount of pressure. They're also very quiet, at least relative to other pumps, and they can be built out of a variety of materials. However, on the other side of the argument, the bushings wear down very quickly in the liquid areas, and clearances need to be very, very precise. That is to say, these packets of fluid being carried around, they cannot go between these two kind of distinct chambers here, as well as where these two teeth mesh together, as where these two gears mesh together. We have to ensure that the gears fit extremely closely, right? We want to pinch the fluid off and spit it out of the pump, not just brush it back into the inlet. Therefore, our clearances must be very tight in terms of the gear and the chassis design. Let's talk a little bit about the math. The quantity of note here is going to be VD, or the displacement volume of the pump. This will be the volume displaced in the small trapezoid chamber seen in these animations here, right? Each of these different trapezoidal containers will have some volume. We can then use this displacement volume to calculate a theoretical pump flow rate in cubic inches per minute in this case. Now, an important note is that this is the theoretical flow rate. The actual flow rate is likely going to be a little lower. We will have leakages that our math just cannot account for. That is why we label this flow rate Q sub T, where the T stands for theoretical. Take a moment to appreciate the calculation done here. Notice we need to know the inside diameter of the gear teeth, the outside diameter of the gear teeth, the length of each of the, or I should say the width of each of the gear teeth in inches, as well as N, the RPM of the pump. If we look at some graphs associated with our external gear pumps, we can notice that the speed, N, that is how quickly we're running our motor, linearly correlates to the flow rate Q. That is, if we increase N, Q will also increase. If we increase the speed of our motor, our flow rate also increases. Now, note over here, when we discussed positive displacement pumps, we mentioned that these pumps do not have their flow rate affected by the pressure. This is mostly true. However, this law fails to take into account the fact that we will have a few internal losses. We can see that theoretically, it doesn't matter what the outlet pressure is, the flow rate will always stay the same. However, this only happens in theory. The actual flow rate, which we will sometimes label Q, or Q sub A, will slowly diminish as our pressure at the output port increases. This is due to leakages, a slowdown of the gear, and heating internally. All right, this is what we commonly refer to as efficiency. As our pressure at the outlet increases, our pump becomes less efficient, and we do actually see a small, but maybe a little noticeable decrease in our flow rate Q. We can define this mathematically as the volumetric efficiency, denoted by mu sub V. This little orange guy here. Mu sub V, the volumetric efficiency, is in units of percent, right? So 80% efficient, 90% efficient, and is found by taking the actual pump flow rate, measured in cubic inches per minute or cubic meters per second, and dividing it by the theoretical pump flow rate, which should be in the same units as our actual pump flow rate. To get our actual pump flow rate, we would perform some sort of experiment. Many of you have seen the flow meter in our hydraulics lab. We would utilize this to find out what the actual flow rate or pump flow rate of our pump is. We would use math to find the theoretical pump flow rate, and then by dividing Q sub A by Q sub T, we would get the volumetric efficiency of our pump. Let's do a little example for calculations involving the volumetric efficiency of an external gear pump. We are told that a gear pump has a 3-inch outside diameter, a 2-inch inside diameter, and a 1-inch tooth width. If the actual pump flow at 1800 RPM and the rated pressure is 28 gallons per minute, which, using this hint, I've already calculated to be 6,468 cubic inches per minute, what is the volumetric efficiency? Well, as we do in previous problems, let's go back and look at our toolbox of equations we have here, namely this one, and find, if we want volumetric efficiency, we need the theoretical, or the actual pump flow and the theoretical pump flow. So I'll go ahead and write that down. So mu sub V is equal to our actual flow rate divided by our theoretical flow rate. Now, we are actually given our actual pump flow, which is 28 gallons per minute. Now, note, I've done this on the wrong slide, but our actual pump flow is 6,468. 6,468 inches cubed per minute. Now, we just need to find Q sub T. Q sub T, we know, is the theoretical flow rate, so I'll come back to my equations. Doesn't look like this one has it, neither does this one, but this one, theoretical pump flow rate Q sub T, can be found by taking the revolutions per minute multiplied by our displacement volume of the pump. Now note here, this shouldn't be per minute, that is my mistake. Our displacement volume should simply be in cubic inches and is found by applying this formula. Pi over 4, the diameter of the outside squared minus the diameter of the inside squared, times L. So I'll come over here and I'll write that out. So my theoretical flow rate is equal to pi over 4 times d outer squared minus the diameter inner squared times the length. And, as it turns out, we have all these values. Plugging this in, right, diameter outer is going to be 3 inches. Our inner diameter is 2 inches, and our length is 1 inch. This will give us 3.927 cubic inches. However, and I've forgotten, as some of you may have noticed, to multiply this by n. Right? That is the speed of our motor. And plugging in for n, we get, right here, 1800 RPM times 1800, giving us a theoretical pump flow rate of 7,068, rounding to a few decimal places, of course. And this would be in cubic inches per revolution. Now, remember, the theoretical flow rate doesn't account for leakage, heat, backflow, right? All that kind of miscellaneous stuff that makes our pump not as efficient as we would have predicted with the math. So, to figure out how good our pump is, we come back over here to our initial formula, right? We had mu sub volume V, which is our volumetric efficiency, Q sub A, which was given as 6468, and divide that by our theoretical, which is 7068, the value we just calculated. Gives us 0.915, or 91.5% efficiency. This means that 91.5% of the energy that we put into our pump will actually end up in the hydraulic fluid. Moving on, let's take a look at our internal gear pumps. Internal gear pumps operate on a nearly identical principle to the external gear pumps. That is to say, the gears create a volume of displacement, right? A small little pocket of fluid that is moved around the gear and forced out at the outlet, right? Oil enters on the left side here at the inlet port, and as the gear teeth move around, this creates pockets of suction, right? These little kind of chambers here that are pushed around to the outlet. Notice this crescent seal, right? That gets highlighted in yellow occasionally from this video that I stole. This seal is important to form these pockets of fluid, right? As this guy rotates around, we see some pockets up here and some pockets down here. But the general idea is that these pockets move the fluid from an area of low pressure down here to an area of high pressure, right? It's carried through these spaces to the point where the constant meshing of the two gears forces oil through the upper outlet port. Now we get a few different benefits and characteristics of the internal gear pump. These are smooth and quiet, and notably, they do not experience as much pulsation. When running external gear pumps, because we're depositing this fluid in these sort of fixed pockets, we get a sort of pulsating pump, right? Imagine like a little heartbeat of fluid. Often, we don't want this, we want a continuous stream of fluid, and that's where the internal gear pump kind of shines over the external gear pump. We get a smoother output of fluid instead of these kind of fixed pumps, these pulses of fluid coming out. The internal gear pump also has better suction capabilities, right? This is especially good for high viscosity fluids, right? That is to say, if you wanted to pump honey, you would first need a really strong pump and a lot of energy, but an internal gear pump would likely be a better bet than your external gear pump because of this good suction capability. And, of course, they are more compact, right? One gear housed within the external gear creates for a much more compact design than having two gears next to each other. The downsides of the positive displacement pump, however, are that they run at lower pressures, they are much more complex and harder to maintain, and they're very sensitive to abrasives or solid-filled fluids. If your fluid does not have or has a lot of particles in it or some kind of slushy or slurry floating around, it will easily damage an internal gear pump. So, how can we fix this? Well, this is where the lobe pump comes into play. The design is nearly identical to the external gear pump. However, instead of a spur gear profile, the gears use a lobe profile, which offers different characteristics. Again, we see here in the animation that these function nearly identically to the external gear pumps. Fluid comes in at this large chamber here through action of suction. It's then pushed around in our fixed chambers towards the outlet, where the fluid is finally pushed out of the outlet port. By altering the gear profile to this lobe-based profile, these types of pumps offer several benefits over external and internal gear pumps. First, they're excellent for viscous fluids, that is, fluids that don't necessarily flow as smoothly, and they handle fluids that contain solids and slurries. Pumps like this are often used in places such as waste treatment plants or water treatment plants due to their ability to handle these solids and slurries. The downsides, however, are that these types of pumps have lower pressure capabilities, they have a larger footprint due to the excessive size of the lobe gears, and they have even more pulsation than the external gear pump. You notice our packets of fluid here are quite large, and as they're deposited at the outlet, create a heavy pulsating effect. The next pump we'll look at is the gerotor pump, which utilizes two gears, a smaller gear which is embedded in a larger gear. This type of pump works on, again, the principle of creating packets of air, first at the inlet port, where by action of suction, the fluid is taken out of a reservoir, packaged into these sort of chambers that rotate around with the gears, and finally deposited at the outlet, where they're pushed or squeezed out into the hydraulic system. These types of pumps are frequently used with automotive systems and lubrication systems because of the following benefits. They offer a compact design. Again, with these embedded gears, it allows a smaller profile, and they function very efficiently. There's very little leakage with these types of pumps, and you get nearly all of the energy that you put into it deposited into the hydraulic fluid. The downsides of the gerotor pump, however, are that they have a very limited solid handling capacity. Your fluid needs to be purely a fluid and really cannot contain any sort of slurries or solids in it. They also have lower pressure and flow rates than screw or external pumps, and they have extremely tight tolerances. Not only does this make them difficult to manufacture, but they are much more sensitive to wear and tear because the tolerances between this inner gear and the outer gear have to be extremely tight. Finally, to wrap up our gear pumps, let's take a look at the screw pump. The screw pump works on an axial direction, which can be helpful for mechanical advantages. That is to say, there are no bending forces exerted on the gear. Taking a look at this animation, the fluid first enters on the inlet port and is chambered off into similar sections as the previous four motors, but this time moved axially along the screw. Again, we see these packets within these chambers of fluid that move along the screw and are finally pushed out to the outlet port. Now, this quite unique design offers a few advantages. It is very smooth and extremely pulse-free. That is to say, unlike the previous
gear-based pumps, the screw pump offers a nearly seamless stream of fluid at the outlet port. They're also very good for high viscosity fluids that need to be pumped at high pressures. And they're extremely quiet and typically don't require a lot of maintenance. The trade-offs, however, are that they're more expensive and quite a deal more complex to build. They're also extremely sensitive to solids, and they are very difficult to manufacture due to the precise alignment required of this primary shaft and screw. To recap, here is a summary of all of the gear pumps we have looked at thus far. Please pause the video and take a look at this table in order to familiarize yourself with some of the best use cases for each of the type of gear pump.